Well, the next talk is by Andrew Reynolds on joint work with Cesare Tinelli, Noetzli, and Clark Barrett. And the title of the paper is A Decision Procedure for String to Code Point Conversion.
Right, so thanks for the introduction. So this is a joint work between University of Iowa and Stanford University. So in the past decade, the theory of strings has gained a lot of popularity in SMT solvers. So strings are important for a number of formal methods applications, including in security for reasoning about SQL injections, as well as access policies in cloud. Yeah. And they have other applications like data processing. Yeah, a number of efficient SMT solvers have been developed for reasoning about strings. So in this work, we developed a new procedure in the SMT solver CVC4, but I've listed several others here. So as an overview of what I'll discuss in this talk, so I'll present a new decision procedure for a simple theory of strings, which includes reasoning about strings with length constraints and a string to code conversion operator, which is the new part of the procedure. And with this operator, we're able to do improved reductions for extended string functions. This procedure is implemented in CVC4, and I'll give our experimental results, which show that the use of this operator significantly improves the state of the art with respect to SMT string solvers. So first, some background. The theory of strings is quite a challenging theory. So just starting from word equations, reasoning about strings with concatenation is RDP space. You add length constraints into the mix. This is the decidability is open. And in practice, we're often interested in reasoning about things like extended functions, like converting between strings and integers, or converting strings to lowercase, and so on, or regular expression memberships. And when you add these in, the problem is undecidable. But regardless, SMT solvers can be efficient for these kind of problems in practice. So if you look inside an SMT solver for strings, it's a cooperation of numerous components put together with the DPLLT framework and Nelson-Oppen theory combination. So on the left, we have a propositional SAT solver. We have theory solvers for uninterpreted functions, linear integer arithmetic, as well as strings. And the portion of the string solver that I want to focus on here is what we call the core string solver. And so this is the portion of the string solver that deals with equalities and disequalities over string terms, including string concatenation, as well as equalities and disequalities involving string length. However, in practice, what a user benchmark may have in it is what we call extended string functions. So I'm giving an example here where I want to convert between a string x and the integer that it encodes. So to give this, the way that the string solver deals with this problem is to give it to the core solver, it reduces it to word equations through a series of reductions, which generates generally a very large formula. And naively, to deal with something like a string to integer conversion, what you have to do is case split on the individual characters of x. So here I'm saying if the ith character of x is 9, then some part of the reduction, I'm not giving the full picture here, is 9. And so what we have is this, it ends up being quite a large formula to reason about these extended string functions. So what we do in this paper is extend the core string solver with now the ability to reason about string to code point conversions. So we have a new operator called code, and what this allows us is to more efficiently and succinctly represent these reductions. So yeah, getting into the theory or the signature of the theory that I'll be focusing on here. So our sorts are, we have the integer sort, int, string sort, and Boolean. The signature is broken into two parts, the arithmetic part and the string part. So in the arithmetic part, we have the usual symbols of linear integer arithmetic, including constants, plus, negation, and linear inequalities. The string signature contains words, L, so string constants that belong to an alphabet, which is denoted A here. We have string length and then a string to code point conversion function code. So what we're interested in is the satisfiability problem for the quantifier free fragment of this theory, where additionally we have equalities and disequalities over each sort. And one thing to note here is that I'm intentionally omitting string concatenation from the presentation here. This is not because we can't use this procedure in combination with concatenation. It's just not the focus, and I'll state a bit later how we can combine this with other fragments of strings. So first, a bit more detail on this string to code operator. So given an alphabet A, we assume an arbitrary ordering on characters, C1 and so on. So for each CI, we call this index I its code point. Then the code function takes a string and returns an integer and is interpreted as follows. So for each string of length 1, W, code of W is the code point of the single character in W. And for all other W, either the empty string or strings greater than length 1, code of W is interpreted as -1. So it has a complete interpretation. So in practice, we're interested in reasoning about Unicode strings. So for instance, strings like A are converted to their ASCII value. But the procedure that we present in the paper is agnostic to this fact, and really you can have any cardinality you want. Okay, so to present the procedure, it's presented in the paper as a rule-based calculus where rules operate on configurations A and S, where A is a set of arithmetic constraints and S is a set of string constraints. And the rules of the calculus are provided in guarded assignment form, where a rule name is given, and at the top of the rule, we give the conditions required for applying the rule. And on the bottom of the rule, we we state the modifications made to the configuration, or alternatively, we denote unsat as being a closed branch. And some rules may have multiple conclusions, which we delimit by this double bar notation. Okay, so more terminology. A run of the procedure generates a derivation tree where each node in this tree is a configuration, and all child nodes are obtained by legally applying a rule to its parent. And given a derivation tree with a given root, a closed derivation tree where all leaves are this unsat means that our root is unsatisfiable. And a derivation tree with a saturated configuration in that there is a node that for which no rule applies, this will mean that our root is satisfiable. All right, so the rules of the calculus are presented in two parts. The first is what we call the core rules, and these are largely adopted from previous work. So our CAT 14 paper has variants of these rules. So I won't go into too much detail here, but just to summarize some of the rules. The first two rules model the standard behavior of a linear integer arithmetic solver in that it is capable of producing conflicts and propagates equalities between integer terms from our set of arithmetic constraints A to S. So this it models the behavior of the standard theory combination mechanism of the SMT solver. The second set of rules here model the core string solver. So these premises here have entailment in the empty theory. So by writing S entails false, we mean entailment in the empty theory, which can be decided by congruence closure. So the core string solver can produce conflicts by pure equality reasoning, and then also is able to propagate integer equalities from the string solver to the arithmetic solver, duly to this A prop rule. The third set of rules is for reasoning about string length. So in particular, we know that fixed strings have a constant length. And the second rule states that all strings are either empty or have strictly positive length. The final rule is a bit technical, but it is used for reasoning about cardinality. So note that because our alphabet is finite, only finitely many strings exist for each length. And so this can lead to certain implied constraints, which I won't get into the details. All right, so we extend these core rules with, it ends up being 4 rules for reasoning about code points. So the first 2 are shown here. So these 2 rules are used for reasoning about the code of a string X, which is, it must be constrained to a fixed value if X is constrained to be equal to a fixed string. Now, we apply this conclusion where I'm saying code of X is equal to code, the evaluation of code of L, where L is a string literal, under 2 conditions. So either X, when X is equal to a constant string of length 1, then we must apply the C intro rule. So if X is equated to the string of length 1 containing the character A, then we add code of X equals 65 to A. The other criteria for adding this equality is if X is equated to a string constant and code of X is part of our set of terms in S. So given some arbitrary constraint about code of X, if X is equal to a concrete string, then we need to apply this C collapse rule. All right, the next rule is C valid. So for each string, either that the length of X is not 1 and its code point is -1, or its length is 1 and its code point is in the range of 0 to the size of the alphabet -1. In other words, it's a valid code point. We do this when code of X is part of our set of subterms of S here. And the final rule is reasoning about the injectivity of code. So code is injective over the domain of strings of length 1. So given 2 distinct applications of code in our set of constraints, then we're in one of the following 3 cases. So either one of the strings without loss of generality assume X is not length 1. We conclude code of X is equal to -1. Or X and Y have different code points. So code of X is not equal to code of Y, or X and Y are the same string. So this rule has 3 branches. All right, so an example of a derivation tree here. So I'm giving an initial set of constraints here at the bottom. Length of X is greater than length of Y. Code of X is equal to code of Y, and code of X is greater than or equal to 0. So first, we can apply the arithmetic prop rule to move this equality between code points to S. So now it's occurring in both A and S. We then apply injectivity of code points to get these 3 branches. In the leftmost branch, we have an arithmetic conflict because code of x is equal to -1 and is also constrained to be greater than or equal to 0. The second branch is also an arithmetic conflict because we're saying that code of x is both equal and disequal from code of y. The final configuration here, we add x equals y to s. And what we get in this branch is that we can propagate to the arithmetic solver that length of x is equal to length of y. And this is also an arithmetic conflict because we said that length of x is strictly greater than length of y. All right, so because this is a closed derivation tree, we know that our root is unsatisfiable. All right, another example here, I'm saying code of x is in the range of 97 to 106. X is not equal to y and z, where y and z are equal to these concrete characters C97 and C106. So by the C intro rule twice, we get equalities between the code of y and z and their concrete values. And I won't show the full derivation tree, but by two rules of two applications of C injectivity, we obtain this configuration, which is saturated. And because it's saturated, we in fact know that the root is satisfiable. And what's interesting is that the model, the string model for x, can actually be determined by the model for code of x. So in particular, in the paper, we give a correctness theorem for this decision procedure. It's terminating, so all derivation trees are finite. It's refutation sound, so a closed derivation tree with root m implies that m is indeed unsatisfiable. It's solution sound, in that a derivation tree with a saturated configuration implies that m is indeed satisfiable. And the important detail here is that the proof of the third fact is constructive. So we actually give a procedure for constructing a model for given an arbitrary saturated configuration. So given these three properties, the calculus is a decision procedure for our theory. So some implementation details. This is implemented in the CVC4 SMT solver as part of its core solver. It's combined with the other procedures in that solver. So conceptually, the way to do this is that the rules with entailment in the empty theory become entailment in some other theory T that we're considering for strings. The strategy is crafted in combination with the other approaches. Some rules are applied eagerly and lazily. The details are in the paper. So what we can do with this is craft some more efficient reductions for conversion functions. So in particular, conversion between strings and integers, instead of case splitting on 10 concrete values, what we can do is construct a linear arithmetic relationship on the code of the characters of x. This is a lot more compact way of reasoning about this. Lower and uppercase conversion, similarly, we have instead of doing a 26-way split on concrete values, we end up with a relationship on code points. Lexicographic ordering, similarly, this can be very compactly encoded using code points. And another nice application of this is regular expression ranges, in fact, fall very naturally into reasoning about code points. So instead of doing a concrete split on the value of x in a regular expression range, it translates directly to inequalities on code points. So for our experiments, we compared a new version of CVC4, which included techniques from the paper, which we denote here CVC4 plus C. CVC4 is the previous version, and we also compared with Z3. We compared against on around 21,000 benchmarks from taken from concolic execution of Python code. These contain string to integer conversions and regular expression ranges. And we used a 300-second timeout. The results look like this. So as you can see, the performance gained from using code points in CVC4 plus C is fairly dramatic. So we go from having 788 timeouts to only 64. And we win just about every row of this table. Not only do we solve more benchmarks, but the runtime is actually significantly improved, which you can see from the top scatter plot comparing the new version of CVC4 against the old version. We also compare favorably to Z3, and the bottom scatter plot shows that comparison, where notice that CVC4 plus C, it's actually slower for very fast benchmarks, but in the end solves significantly more benchmarks in the end. All right, so to summarize, I've presented a new decision procedure for string to code point conversions. Supporting this code operator allows us to encode these extended functions in efficient ways. So the procedure is implemented in CVC4, as I mentioned. It's combined with other procedures, and you can use it, in fact, in combination with any of the other theories supported by CVC4. Yeah, as I mentioned, the experiments show that supporting this operator leads to quite a significant improvement in CVC4. So for future work, we plan to support more extended functions. So because now our core solver is capable of handling these more expressive constraints, this may allow us to broaden the range of user extended functions of interest to users. We're also working on making the string solver in CVC4 proof producing. And so that's the end of my talk. Thanks for your time.
Thank you very much. So there is the time for questions, and we have a question by Martin Lester. One moment. So Martin, you should be able to ask your question now.
Hi, I don't know if you can hear me.
Yes, I can hear you.
Great. Yeah. You say this is for Unicode strings, and often when you have Unicode strings, they're encoded in, say, UTF-8, where you have some characters that are multi-byte. But you might have a situation where, for security verification or something, you know what length a string is going to be in terms of number of bytes of the encoding, but you don't know where the string boundaries are going to be, where the character boundaries are going to be, and you don't know how many characters are going to be in the string. So I wondered if you had any ideas how you might be able to support that.
Yeah, so I mean the reason why I say Unicode strings is actually the SMT-lib standard is now in terms of Unicode. So actually this is kind of a question more for in terms of the SMT-lib standard, what kind of constraints different encodings of characters would be supported. But yeah, in theory, you could use any number of ways of encoding this. Now there is another aspect of string solving. There's a theory of sequences actually that we're looking to support, where potentially you could be reasoning over strings with different element types. So where characters can actually be arbitrary data. So this could be another way of addressing these encoding issues.
Okay, thanks.
Okay, thank you. Are there further questions? So, I mean, you gave a comparison, an experimental comparison with Z3. What about a comparison of the techniques? So does Z3 handle strings and string-to-point conversions in the same way as you presented in your paper, or what are the main principal differences in the techniques?
No, so as far as I know, the Z3 does these more basic reduction techniques, as far as I know. I mean, in fact, this string to code point conversion is actually quite a new operator. It was just added to the standard. So yeah, as far as I know, they implement these reductions similar to how they used to be done in CVC4.
Oh, I see. Okay. Are there further questions? That's not the case. So thanks again for the very nice talk.